All righty, lads and ladies, welcome back to college algebra. Let me get some of these things out of the way. We can get started. Oh, there we go. So we're going to need the document to come up. Turn this picture. Oh, there we go. Oh. So I was looking at the course schedule, trying to decide what to do today, because normally in college algebra, I don't begin the unit on systems of equations and systems of inequalities until next week. So we're actually a tiny bit ahead of schedule, which I figured meant we can slow the pacing down just a little bit and spend a smidge more time talking about logs and exponentials, just to make sure everybody's as comfy as they possibly can be. So I did go ahead and extend the homework set, homework 19 and quiz 19 through to next Tuesday. And I figured we could begin today by taking some questions from that homework set or anything else to do with logs and exponentials, spend some time looking at graphs, try to get sort of a holistic view on what it is we've been doing to make sure that we don't leave in a hurry while there is still stuff that you guys would like to talk about. So that's the first thing we're going to do today. I guess we should say here, this is MAC1105. Section 015, it is a college algebra class. And that the date today is the 7th of April, 2022. So I figured today we could talk a bit more about logs and exponentials. And then we are going to introduce systems of equations. Which is one of the last two units in the class. So the last two units in the class are systems of equations and systems of inequalities. But since we have a total of, I think, 3, maybe even 4 class periods left before the final, we do like to reserve one of those for review. We can spend a little bit of time today wrapping up logs and exponentials. So yeah, as Samantha and Emerlyn have begun to do, if you could just go ahead and send me in chat, I think those are DMs, so you guys can send. Go ahead and send me in chat anything that you guys would like to see relating to logs and exponentials. Could be from homework 19 or homework 18. I think this goes back as far as homework 16, the whole kind of, even homework 15. So anything from homeworks 15 through 19 that you guys would like to see or you think would be helpful to talk about, I would be happy to work with here. I do see a few problems coming in from homework 19, so I'll go ahead and open that up. All right, and if I'm going in order here, the way the questions have come in, number 6 was the first one. So we're told that a radioactive element has decayed to 1/16 its original concentration in 10 minutes. And we're asked, what is the half-life of this element? Let's start there. Homework 19, problem 6. This is a cool problem because it's not identical. It's not like a cookie cutter half-life problem. Normally, because of the way these things show up in real life, we have the information about the half-life of the element, and we use that to learn something else. Here, though, they have some other information about the element. They have an amount of time it took for the element to decay to 1/16 its original mass, and you're asked to find the half-life. So I applaud the ingenuity in the problem writing here. Let's see if we can figure out where to begin. So what sort of clues are there here in the problem that might suggest a good starting place? And then we'll see where to go from there. But let's ask first, just what do I even begin with? Are there any hints as to where we could get started, just writing something down related to the problem?
Just write down the equation first.
Yeah, let's start. So we know we have a function that models half-life. Right? This guy. This guy is the function that tells you if you've got something with a half-life k and you allow x units of time to pass, if the original amount was c, this will output how much is left after x units of time. Usually we measure time here in years. Right, remember each of these parameters has a meaning. X is the time that has passed, K is the half-life of the substance, and C is the original or initial amount. We weren't given the initial amount or the original amount, but we were told that this element has decayed to 1/16 its original mass in 10 minutes. So let me first check and see the units they want the answer in here. They want the answer in minutes, so we can use minutes for time throughout the problem. We don't need to convert into years or months or anything. So 1/16 of the original amount. This would be 1/16 times C. It's okay that we don't know what C is. We're just describing the relative change. We're talking about, how much how much remains in terms of the original mass. So they told us that 1/16 of it remains. So I'm going to do something with this function and something with this output from that function. We can also say that 10 minutes after beginning, there should be f of 10, which would be c times 1/2 to the 10 over k, whatever grams left. All right, that's just following the model. The model says plug in a time for x, and this will tell you how much of that shit is left. So between these two bullet points, we have two ways of measuring how much stuff is left after 10 minutes. On the one hand, they told you that 1/16 of the original amount was left. On the other hand, you have your half-life function, so you can plug in 10 minutes to that function, and this should be how much is left. So these are both measuring the same thing, which means you can set them equal. And that's what we're going to do. We're going to set C times 1/2 to the 10 over k equal to 1/16 C. You can divide both sides by C. And that gets me here. My goal is to find k, which is the half-life. So what would be a good next step in solving this exponential equation for k?
Taking the natural log of the two to bring the 10 over k down.
Yeah, excellent. I can take logarithms on both sides, and taking the natural log, I agree, is the kind of nicer way to do it. You can take whatever base log you want. Everybody and their mom uses the natural log. So that gives me this. And then, like Tyson said, the reason we're going to do that is because it allows me to bring this exponent, the 10 over k, down out of the power in front of the logarithm. That's sort of the mechanical beauty of these functions. All right. A bunch of ways to solve for k from here. Any thoughts?
Divide the ln over 1/2 over.
Good. So that natural log of 1/2, he's definitely in the way of k being alone. And that'll give me 10 over k equals the natural log of 1/16 divided by the natural log of 1/2. Okay, what now? Put my k down here. When I look at this, what jumps out to me is that when solving for anything, solving for k in particular, we need it to be upstairs, right? We want it to be alone and upstairs. So how about I take reciprocals on both sides? You know, that's a valid operation, taking reciprocals. Or flip both sides. And that'll bring k up from the bottom to the top where I want it. Brings the 10 down here and just flips this whole ratio over. So now the natural log of 1/2 will be upstairs and the natural log of 1/16 goes downstairs. I just flip both sides. Okay, what's my last step going to be? I want to solve this for k.
Multiply 10.
Yeah, good. I can multiply both sides by 10. Okay, there are some things we could do algebra-wise to clean this up. The natural log of 1/2 is the negative ln of 2. Natural log of 1/16 is the negative ln of 16. There's little things we could do, but not much. And no reason to stress. We can just go ahead and work with it as it is here. This is the correct answer. I'll take 10, multiply that by the ratio, ln of 1/2. Close parentheses, divide by the ln of 1/16. And that gives me, ooh, that's a nice, neat number, exactly 2.5. That's rare. Of course it is. Okay, I see. So this is 2.5. And what are the units here? 2.5 dogs or cups of coffee or light years, millennium,
Minutes.
minutes. Yeah, good. This is a time. And throughout the problem, we've measured time in minutes, so we can be confident that this is measured in minutes. Any questions on the setup or how we solve this bad boy?
Can you explain why you flipped it again?
I want to solve for this k. So at some point, I need to do something to bring k upstairs. So flipping both sides is one way to bring k upstairs. Another way we could have done that from here is to cross multiply by these denominators. So I could rewrite this as 10 times the natural log of 1/2 is equal to k times the natural log of 1/16. This is sort of the other natural way to do this. And then you can divide both sides by the natural log of 1/16. Either one would work, but that operation, flip both sides or take reciprocals on both sides, it's a nice operation. So I just wanted to demonstrate that. But anytime we're going to solve for a variable, we need to get it upstairs. And that can be done a handful of different ways. One of these two things must be done. If you wanted to, you could break the green down to even more granular steps. You could multiply both sides just by k. So the first green step, what I did is I multiplied both sides by k to bring the k over here. And I multiplied both sides by ln of 1/2 to bring that over here. You could just multiply both sides by k, and that would give you 10 equals k times this fraction, and then just divide over by this big fraction if you wanted. You could do them in more broken down steps if you like. But yeah, this is a nice thing. It's true. If x is equal to y, that means it's equivalent to 1 over x is equal to 1 over y. As long as the things are non-zero, you can always flip both sides.
Okay, thank you.
Yeah, of course. Other questions or comments on this one? I did see, I think I got this from 3 different people, so.
I just need help like separating if it would be not 10 over k, just 10k, and trying to separate k by itself. I forgot how to separate it. I think I put a question in there where I was having the problem at.
Let's see, so if we had something like 10k equals the natural log of 1/16 over the natural log of 1/2.
I know you would divide both sides by 10, but I'm just confused about whether or not the 10 would be on the denominator or the.
Yeah, that's a good question. So we run into this sort of stuff a lot. How do we deal with dividing a fraction by something else? It can be a little wonky. So it's true, we can divide both sides by 10, right? And I think what most people would come up with there is something like ln of 1/2 divided by ln of 1/16 divided by 10. But there's a big problem with expressions like this. So I'm going to put a pause on this. We're going to come back here. This isn't quite correct as it is. It's not that it's wrong necessarily, it's just that it's missing something. These are different. 10 divided by 2 divided by 5 with the top in parentheses is not the same as 10 divided by 2 divided by 5. Division is such a weird operation because it's not associative. 10 divided by 2, the upstairs here, this guy is 5 over 5, which is just 1. 10 divided by 2/5, this is the same as 10 over 1 divided by 2 over 5. Because the 2/5 is in parentheses here, this says I'm taking the number 10 and dividing by 2/5. So the way I handle this is by thinking of 10 as 10 over 1, and then we can flip and multiply. So this would be 10 over 1 times 5 over 2, which would be 25, right? 10 times 5 is 50, divided by 2 is 25. So see, the way we handle division when you've got the kind of stacked division, these so-called compound fractions, it's all about what you do with your parentheses. Sort of what's the big fraction bar. That's the way I see it taught in like high school and stuff. They'll put a big fraction bar here, and that's supposed to tell you where the parentheses go, but that's shitty notation. Just remember that you started with this fraction over here, and you want to divide this fraction by 10. So that means that that fraction should go in parentheses, and you want to divide the whole thing by 10. And that means what we're looking at here, 10 is the same as 10 over 1. So when you have a compound fraction, especially with 3 parts, right? If you've got like 4 parts, it's kind of easy to tell what's going on. If you've got 2 parts, there's no compound fraction. If you have one with just 3 parts, like either the 2 purple things here or the thing that we're trying to wrestle with here, the trick is actually to write it with 4 parts. Figure out where the big fraction bar is, and then write the top and bottom of the big fraction as little fractions themselves. So this 10, I'm going to write as 10 over 1 in the same way I did here. So now I'm dividing one fraction by another fraction, and we know how to do that. You leave the top alone, flip and multiply by the bottom. This. And that means that in the end, right, when you take this thing, in the end, the 10 is going to be downstairs, because now we know that this is the same as this, and I can just multiply the top with the top and the bottom with the bottom. So we've got the natural log of 1/2 divided by, I'm going to put the 10 in front, 10 times the natural log of 1/16. I'm glad we looked at this. This issue with the non-associativity of division, I know that makes it sound more complicated than it is. Just not knowing where the big fraction bar is in a fraction with 3 parts can be quite flummoxing. I remember this bothering me all the way up through Calc 1. And then finally in Calc 1, I was like, oh, this is the trick, right? Always, if you've got a compound fraction, figure out where your parentheses are. Figure out sort of where the big fraction is, and then make sure you write the top and bottom as individual little fractions themselves. And playing around with stuff like this can help a lot. It's good. Other questions on this one? Okay. The next one that was requested was number 7. We have 650 grams of an unknown radioactive substance that decays according to this function, where t is measured in years. How long before half of the substance has decayed? So in other words, it's again, we want to find the half-life. But this time, we've been given a different kind of function, one that does not look like a half-life function. I'm not going to write all the words here. D of t is 650 times e to the negative, 0.00 MAC1105 times T. Now we want to find the half-life. Okay. So what I would really like to do is rewrite this as a half-life type function, right? I'd like to rewrite this as a function with the base 1/2. One way to do this, let me phrase it the way the problem phrases it. How long until half? Right, which is the same thing. Same thing. My initial amount here is 650. So half remains when d of t is equal to 650 times 1/2. So I'm going to take this function and set it equal to 650 times 1/2. And kind of like we've seen in a lot of these problems, our first step is going to be to divide by this constant. So that initial amount is going to drop out of the expression on both sides, and I get e to the negative 0.004715 times t equals 1/2. All right, how would I solve from here?
Take the natural log of both ones,
Very good.
both sides.
Yeah, I always think of this. I know it sounds silly, but there's a part of my brain that kind of feels like I'm at a football game or something, you know, and just like cheer, take logs. It's ridiculous, I know. But it's this amazing new operation. We should be very proud of it. So yeah, when we get here, we're going to take the logarithm on both sides. It's this badass new tool we have. Definitely going to use the natural log here. On the left-hand side, we could bring this down. But there's an even faster way to simplify the left-hand side. I'll go ahead and break it down. We'll treat it the same way we've treated all the other ones. But because the base of the exponential here is e, and we're using the natural log, which is the base e log, you're going to see this left-hand side clean up very, very nicely. What is the natural log of e? So normally we would divide over by this, and then divide over by this, and we've got ln. In this case, though, it's even nicer because this number, we don't need to carry this around. We know what this number is. What is the ln of e?
1.
1. Very good, right? The natural log is the base e logarithm. So we're asking to what power must you raise the base e in order to get the inside, which is also e. That's 1. Good thing to know, the natural log of E is 1, which means the left-hand side is really just negative 0.004715 t, and the right-hand side is the natural log of 1/2. So now I can divide over, so 1/2 divided by negative 0.004715. And this is a case where we do want to use our calculator, get a nice decimal here. I'm getting 147.0089, blah, blah, blah. And call it 147.01. And I think we're measuring time in years here, right? Yeah. Questions on any of these steps or how we need to set it up like this? Anything at all?
How did that 650 cancel out again on the top?
So from here to here, I divided both sides by 650. Cancel, schmancel, cancel, schmancel.
Okay, because at the start you're setting them both equal to each other.
Yeah, so they asked us how long until half of the original amount remains. We know that the original amount was 650 grams from here, right? This constant out front is always the initial amount. So they said, how long until half remains? So I go, okay, how much is half of the original amount? Well, if the original amount was 650, then half of the original amount is 650 times 1/2. So I set this function, which tells me how much shit is left, equal to half of the original amount, which is 650 times 1/2. So I'm going to set this function right here equal to 650 times 1/2 right here. I feel comfy. Other thoughts on this one? Okay, let's move to the next one. I think the next one was number 9, and I had a few requests for that. And then there's also a specific equation here. So let's take a look at number 9 from the homework, and then I'll come to your equations then. Yeah, I thought about doing this one in class the other day. I thought this was a cute one. Because this is such a cute problem here, number 9, I would like to get a little bit of input from you guys. So we've got 15 to the x equals the cube root of negative 125. We want to solve. Did I write that correct? Yeah, okay. So first, what is the cube root of negative 125? Who can help me with that?
And the cube root to 125 is 5 times 5 times 5.
Mhm.
It's -5.
Very good. 5 cubed is 125. So if you take -5 and you raise that to the third power, that's -5 times -5 times -5 is going to be -125, which means that the cube root of -125 is -5. Right? That's the way roots work. So if you don't know that the cube root of -125 is -5 off the top of your head, you could come up with it by thinking like this. It would require a bit of guesswork. The number ending in 5 tells you it's got to be a multiple of 5. So you could divide 125 by 5 and discover that you get 25. 25 is 5 times 5. You could get there like that. There is also a way to enter this in your calculator. You notice that if you hit second and then the square button, you just get a regular square root, right? Which is not what we want. We want a cube root. There is a way to get there. If you hit the math button and then scroll down to this, you've got a dedicated cube root function here. You've also got an x root here. So of course we could use the cube root function. If we wanted to use the x root function, you'd have to type 3, then math, then go down to this, and that will give you a cube root. But you could also use the dedicated cube root function there and see that this works. Okay, so then what I'm going to do is rewrite my equation, 15 to the x equals the cube root of -125 as 15 to the x equals -5. Because I'm just simplifying that right-hand side. Okay. There is something subtle that I'm going to come back to regarding this equation, but let's not worry about that for now. What would my next step in solving this equation be?
Take the the natural log of both sides to bring that x down.
Yeah, right. And take logs. Now at this stage, alarm bells should start going off. You should smell toast. But we can proceed. It's not jumping out yet. We know that the reason we take these logs is to bring the x down. So I'd have x times the natural log of 15 equals the natural log of -5, more alarm bells. And just kind of, again, mechanically following the steps, you would divide both sides by the natural log of 15. Now, when I go to type this into my calculator, it's going to poop the bed. Why is my calculator going to poop the bed?
Because you can't take the ln of a negative number.
Very good. The numerator there is undefined, right? If we type this, it's going to tell me that there is a non-real answer because this numerator is undefined. Very good. So what do we conclude? We did everything right. Well, let's back up to this equation here and take a look at it the way we were looking at these before using the calculator, by thinking of it as the intersection of two curves. I can graph y1 equals 15 to the x and y2 equals -5 and try to see where these hit, if anywhere. I'm going to change my x min and x max, just zoom in horizontally a little bit. There's 15 to the x, there's -5. These things are never going to touch each other. This thing, the curve up here, is never going to be equal to this thing, which horizontal line down here. So this has no solution. Fifteen to the x is always positive. So 15 to the x could never equal -5. So this is an equation with no solution. A nice thing to remember, one of the properties we discussed for exponential functions b to the x is always positive, regardless of the base. Those graphs either look like this, if b is bigger than 1, or like this, if b is less than 1. But no matter what, it'll never poke down below the x-axis. Right? The graph always lives entirely above the x-axis. So this thing never going to be negative, always going to be positive. Okay. Let's look at a quick variation on this just to see, because here it's kind of unsatisfying, there's no solution. But there are very similar looking problems for which there are solutions, and you don't even need the thing on the right to be a perfect cube. I could ask us to solve something like 4 to the x equals the, how about the cube root of 120. Now 120 is not a perfect cube. So I'm not going to be able to simplify the right-hand side as nicely as we did on the last problem. But 120 is positive, so its cube root is positive. So there is a solution here. All right, I can play the same calculator game. Clear that out, it's fine. And here I can type cube root of 120. Oh, I might need to zoom out. Oh, no, we got it. So there is going to be a solution here, right? These curves do touch. Looks like it's going to be somewhere around here between 1.06 and 1.17, somewhere in that range. How do we find it? Actually, we don't even need to do that. We could, what I was thinking is we could write this as 120 to the 1/3 power if we want, although it's not necessary. But the next step is definitely necessary. And it's the same magical step that all of these problems share. We want to take logarithms on both sides. The only reason writing this as 120 to the 1/3 is nice is because I can also bring this power down on the right. And that's kind of slick. It makes the answer look prettier, but you don't have to. You could just leave the right-hand side as the cube root ln of cube root 120 if you want. The big deal, of course, is on the left-hand side, you get x times the ln of 4. Over here, I will bring the 1/3 down because it just looks nice. That inside be a regular ln of 120. And then I would divide over by the natural log of 4. Now we asked some fun questions about fractions earlier, so let me ask a similar sort of one here. Are these the same? There is no difference, Kylie. You could use either one. So I use the natural log as I go through solving these problems for a handful of reasons, mostly because I'm trained as a number theorist. So the particular field of math that I work in, we use the natural log for everything. We never use a base 10 logarithm because they're just not as convenient. The number e shows up in so many unexpected places that if you have to pick a base to use for your logarithm, it's nice to use the base that kind of shows up naturally everywhere. Also, in calculus, the base e exponential and the base e logarithm, the natural logarithm, have a bunch of really nice properties related to the calculus operations of differentiation and integration. So usually once you learn a bit of calculus, you develop an affection for the natural log and the number e. But you could use the log log here without any problems. Everything would be the same. Just everywhere you see ln, you'd write log instead. And that's true for all the problems that we've looked at. So is the purple here equal to the green here? Does anybody want to hazard a guess?
No, because wouldn't you have to multiply by the whole thing instead of just bringing it down to the 1?
It's an interesting question. So there's a handful of approaches to this. So this is a true statement. Let me first do this the brute force way. Let's write parentheses 1/3, close parentheses, times the natural log of 120, close, close. So there's my whole numerator here, right? Carefully written out in parentheses. And then divide that all by the natural log of 4. So this looks like it's about 1.15. And on the other fella, I can take the natural log of 120 and close paren, divide. We got to open up parentheses here because the downstairs is 3 times the ln of 4. We want to make sure that all stays in the downstairs. So open parentheses, 3 times ln 4, close, close. And we get the same thing. So these are actually equal. One way to see it, and learning how to juggle all of these weird types of fraction expressions, it just comes with practice. One way to see this is to realize that having a 1/3 upstairs here is the same as having a 1/3 out front here. Kind of the rule we're using there, that A times B over C is the same as A over 1 times B over C is the same as A times B over C. So here A is the number 1/3, B is the natural log of 120, and C is the natural log of 4. From here, we now are multiplying two fractions, so we can multiply straight across. 1 times the natural log of 120 is just the natural log of 120, and 3 times the natural log of 4 is 3 ln 4. So it might not look like it. It might look like this and this are pretty different expressions, but a 1/3 upstairs is the same as a 3 downstairs because we can play this game. But however you write it, just be careful when you put it into your calculator. You notice both entering this and entering this, I had to put some parentheses in the calculator that we're not writing down up here. So another good tip in your calculator, always put the top and bottom of fractions in parens. Fraction bars imply these parentheses. And when you enter things into the calculator is dumb. It does not know what you wrote down. It does not know your fraction bar was long. It just follows the order of operations very blindly. So if I just typed 1/3 ln 120 divide by 4, that would be different than 1/3 times ln of 120 all divided by ln 4 from the perspective of the calculator. And same thing with this one. Watch this. If I type ln 120 close paren divide by 3 times ln 4, what do we think? Is this going to come out to that same 1.15? Let me clear this out so we don't have so much distraction. ln 120 close divide by 3 times ln 4. Do you think this is going to come out the same as that green expression? It looks like it, right? Watch this. It's not. So what's going on with the calculator here? What's going on here is that the calculator is doing the order of operations the way you learned in grade school, straight left to right, because multiplication and division are in the same tier, right, in the order of operations. So this is going to do ln of 120 divided by 3, and then multiply that result by the ln of 4. So it's going to treat this like ln of 120 divided by 3 times the ln of 4. That's how the calculator reads that. So if you type it just like this, then the ln of 4 is actually upstairs when the calculator reads that. So to get this correct, we need to put the bottom in parentheses. And the safe path here is just always put the top and bottom of fractions in parentheses. If there's more than one term, always put the top and bottom in parentheses. Now you'll get your 1.15. Okay. There was one more thing here that was requested. We want to solve a particular log equation. So let me go ahead and do that. And then I'm going to introduce the ideas of next week's material, which is systems of equations. So we wanted to solve 3 plus the log of 16x equals 15 minus the log log of x. That's kind of interesting. Any ideas what I could do here?
You can subtract the 3 over, right?
Yeah, that's a good start. Let's get this 3 over there. So that'll give me the log of 16x equals 15 minus log x minus 3. And the 15 and the 3 are like terms. 15 minus 3 is 12. Okay, good so far. Well, now. It's kind of weird, right? Because we say you need to isolate the log term and then exponentiate to solve these log equations. But there's 2 log terms. There's this one, which has a variable inside of it, and this one, which has a variable inside of it. We looked at one problem like this at the end of class last time. Does anybody remember the trick?
If they had the same base, they could cancel out and you're just left with the numbers, right?
If the 12 wasn't here, that would work. If there was no 12 minus, if I just had log 16x equals log x, then we could basically ignore the logs. That's true, using the 1-to-1 property. But we have this 12 and this log is being subtracted, so that won't work here. And normally the way we get rid of a log is by exponentiating, but we have to combine all the logarithms. We have to isolate a single log term with our variables in it before we can exponentiate. So the move here, we're going to add this to both sides and then find a way to combine the 2 logarithms. So I'll have log of 16x plus log of x equals 12. And then using that addition outside is multiplication inside property. I can put those 2 logs together. We just multiply the insides. So what we end up with is the log, the base 10 log of 16x squared, x times x, equals 12. Now I'm in a place where I can get rid of the log. How do I get rid of this log?
Base 10.
Yeah, it's a base 10 log, so I'm going to exponentiate on both sides base 10. In other words, I'm going to put both sides in the exponent of the number 10. Now 10 to the 12 is an enormous number. It's a 1 followed by 12 zeros. So I'm just going to leave 10 to the 12 as 10 to the 12. But on the right-hand side, something nice happens. The 10 and the log cancel, right? This is like f of f inverse of some stuff. So the left-hand side just becomes 16x squared. The right-hand side is 10 to the 12. From here, I can divide both sides by 16. still a giant number, right? 10 to the 12 divided by 16 is still too big to write down in its normal decimal form. So we'll just leave it like this. And then I can take the square root on both sides. And when I do that, I'm going to get a plus and a minus. Square root 10 to the 12 divided by 16. And that number we actually can clean up quite a bit. That's the square root of 10 to the 12 divided by the square root of 16, and our plus and minus is out front. Downstairs, the square root of 16 is 4. Upstairs, the square root of 10 to the 12 is 10 to the 12 over 2 is 10 to the 6. So we get plus or minus 10 to the 6 over 4. 10 to the 6 is 1 million. And ostensibly, we have two answers. One of them is extraneous. Because the original problem has the log of x in it and the log of 16x. Both of these would be undefined if x is negative. We're just going to hold on to the one solution, the positive one. And that's our only solution. Now, if you got to here and you said, I'm just going to take the positive square root of 10 to the 12 over 16, I would accept that also. If you just gave me this as your answer, I've got no problem with that. Or if you wanted to actually compute 10 to the 6 over 4, that's a pretty reasonable size number. 10 to the 6 is what, a million? So 1 million divided by 4 is going to be 250,000. So either this form of the answer, this form of the answer, or writing out the whole number at 250,000, all of those would be okay. Questions on any of these? So I want to go ahead and introduce just a tiny bit where we're going. Next week, we're going to talk about systems of equations. And these come in a few different varieties. You can talk about linear systems and nonlinear systems. We'll do formal definitions and all of that later. I want to start just with an example here. Suppose I want to find two numbers, call them x and y, such that x plus y is equal to 10, so two numbers that add up to 10, and x minus y is 2. So you can phrase this purely as a question about numbers, right? Can you find two numbers that add up to 10 and subtract to 2? The nice way of thinking about this is to think of each of these as graphs, as lines. So x plus y equals 10, that's the same as saying y is equal to 10 minus x. And x minus y equals 2 is the same as saying, let's say I can add y, I'll do it like this. Negative y is equal to 2 minus x. This is what most people would do. And then y is equal to negative 2 plus x. If I graph each of those lines, 10 minus x, we'll call this 10 up here, is a line with slope negative 1 and y-intercept 10. Here's that first line. And negative 2 plus x, we'll call this negative 2, is a line with y-intercept negative 2 and slope positive 1. X-axis, here is y-axis. So graphing these two lines, there is a point here that is kind of interesting, and that's the point where they touch. That point where they touch is an ordered pair, x comma y. And because it is on the first line, it must be true that when you take this x and this y and plug it in here, you get a true statement. Also, because it's on the second line, it must be true that when you take this x and this y and plug it in here, you get a true statement. So it means that this ordered pair A comma B solves both equations at the same time. And that's what we call the solution to a system of equations. So a system of equations is a set of equations meant to be solved simultaneously or at the same time. If you have two equations, each one having two variables, that means what you're looking for is an ordered pair. You're looking for both an x and a y that satisfy both equations at the same time. Now, do I know what this number is from the picture I've drawn? Nope, I don't know what this x value is here, and I don't know what this y value is here. I can say a few things about them from the picture. Definitely it's true that they're both positive, right? This point lives in quadrant 1. So both the x value and y value are positive, and we can be sure of that, even if my picture is not perfect. It looks like the y value is somewhere in the neighborhood of like 4 or 5. It looks like this x value is somewhere in the neighborhood of like 3, but 3 plus 5 is not 10, so it can't be exactly that. There are a lot of ways to solve this, to find this for sure. We can estimate from our graph. From our graph, we can be sure that there is a solution. That's pretty cool. And one way to find the intersection is called substitution. So I have these two equations here, right? Y equals negative 2 plus x, and y equals 10 minus x. I can take 10 minus x and plug it in for y here. we need both of these to be true at once. So since y is equal to 10 minus x and y is equal to negative 2 plus x, we can plug this guy, 10 minus x, in for y here. So we get 10 minus x equals negative 2 plus x. By taking this and plugging it in for y there. I can add x to both sides. And add 2 to both sides, and x plus x is 2x. And then I can divide both sides by 2. So that x value is 6. And then to find y, I can plug x equals 6 into either original equation. So I'll plug it into y equals 10 minus x. This will become y equals 10 minus 6, which is just y equals 4. Oh, 4, that was what we guessed for the y value. That was actually correct. So in other words, this ordered pair here is the ordered pair 6, 4. Those are two numbers that add up to 10, and when you subtract them, you get 2. And when you have them in your hands, it's very easy to say, oh yeah, of course those work. But coming up with them just from the words of the problem is quite difficult. That's the true power of systems of equations. They let you take fairly complicated sounding problems and kind of break them down into little compartments. Each kind of rule or restriction that the problem tells you gives you a new equation. And each sort of a variable or degree of freedom or option that the problem gives you, that gives you another variable in the equations. There's a whole big field of mathematics called linear algebra that studies systems of equations. It might seem like it's a little bit boring, like why would someone spend their whole life doing that? But you generalize and abstract very quickly. This is actually the mathematics behind quantum physics. It's all operator theory, which is linear algebra, which is the field of math that kind of grew out of studying systems of equations. It's very beautiful. I'm not going to spend any more time on this here. We're out of class time today, but I wanted to give you a little introduction. I think most of us see something along these lines somewhere in high school. And for the remaining part of the class, we're going to be studying systems of equations. So stuff like this. On Tuesday of next week, I will introduce the sort of standard terminology and notation for a system. We're going to talk a little bit more about solving using substitution. That's this method. But then the rest of the time, we're going to talk about using another method called elimination. So that is it from me for today. I'm not opening up a fresh homework set. You can start on the systems homework if you want, but I don't expect you to. Please just take the time to polish up any of the exponential and logarithm stuff that you need. Homework 19 has been extended through to next Tuesday, along with the associated quiz. If you need more time on any of the homework 15 through 19 stuff, please let me know, and I'll go ahead and pop that open. Otherwise, enjoy your weekend, stay safe, and I will see you guys on Tuesday.